So in this video what we're going to do is have a look at two terms, empirical and molecular formula, and you may have come across these at school. So empirical formula and molecular formula. Now what's really important to remember when asked what an empirical formula is that it's the simplest whole number ratio, but much more important, we need to be able to see that you can say of atoms of each element present. Atoms of each element. Whereas molecular formula is the actual number of atoms of each element present. So if I were to take a formula like the formula of butane, C4H10, that would be its molecular formula. There are actually 4 carbons and 10 hydrogens. But what would its empirical formula be? Well, its empirical formula would be C2H5, because that's the simplest whole number ratio. So how would you find this thing called empirical formula? Because normally you wouldn't actually have the formula to simplify. You'd be finding the empirical formula from experimentation. In chemistry we would find the empirical formula and then we would scale up to the molecular formula. So how do you calculate empirical formula? We've set out a little table here to help you. In order to calculate empirical formula, to calculate the simplest whole number ratio of atoms, you need to know the ratio of atoms, and to do that in chemistry you need to know number of moles. So we're going to have to calculate the moles of each thing in order to find the ratio. The masses we can't just ratio because different things have different molecular masses, so we need to convert into moles before we ratio. Now what you might find helpful is there's a little haiku that you could remember that goes, convert mass to mole, there's your 5 syllables of your haiku, divide it by the smallest, there's 7 syllables. So we're going to convert mass to mole, we're going to divide it by the smallest, and then we're going to multiply till whole. We're going to scale it up till we get whole numbers, because it's the simplest whole number ratio. So let's have a go. Here we've got some numbers. We've got 3.2 grams of sulfur, so I'm going to put that in here, 3.2 grams. And we've got 3.2 grams of oxygen. So don't be fooled into thinking that the ratio is 1:1, because they're not the molar ratios. If you go to your periodic table, you'll see that sulfur is 32.1 and oxygen is 16.0. So to convert mass to mole, that's our first line. Then if mass is Mr. moles, then moles is mass over MR. So we're going to take our top number and divide by our bottom number. So get your calculator out now and find that out. So there you go. If you've converted the mass to moles, you should have those two numbers. And then the next line of our haiku says, after convert mass to moles, divide it by the smallest. So who's smallest? The sulfur moles or the oxygen moles? So I'm going to divide it by the smallest, which is the sulfur moles. So if I divide sulfur by the smallest, then obviously you're dividing by yourself there, so you're going to get the number 1. And if you divide 0.2 by 0.0997, then you're going to essentially get the number 2. At this point we will round. Up until this point it's important to keep some significant figures, at least 3, so that you know that your answer is working out properly. And we've got 1 S and 2 O's as our empirical formula. So have a go. Convert mass to moles, divide it by the smallest, multiply till whole. I've converted the masses to moles, and now I'm going to divide by the smallest. So if I divide by 0.04, this is going to be 1. But if I divide this by 0.04, this is going to be 1.5. So now I'm going to multiply till whole. So what would I need to multiply these numbers by to get whole numbers? I'm going to multiply by 2, and I'm going to get a 2 and a 3. And so my empirical formula is going to be P2O3. So I multiplied until I got whole numbers. It must be the simplest whole number ratio, so you can't just say if I multiply by 10 I'll get 10 and 15, because that's not the simplest whole number ratio. We're looking for common fractions here, so if you're not too sure, you need to make sure you know your common fractions so that you can spot them. Okay, so our common fractions are, if it ends in a 0.25, that's a quarter, isn't it? So we're going to multiply everything by 4 to get whole numbers. If our number ends in a 0.33 or something similar to like 0.34 or 0.32, then we're looking at a third, and we will want to multiply by 3 to get whole numbers. If we see something that ends in 0.5, we can usually spot that as a half. It might end 0.49, but that is essentially 0.5, and we're going to times by 2. If we see 0.66 or 0.67, that's 2/3, and we'd multiply by 3. And if we see 0.75 or 745, then we're looking at 3/4, and we would multiply by 4 again. So make sure you know your common fractions, how they appear as decimals, and what you would multiply by. Here's a slightly different one because we've been given the mass of lead, but we've then been given the mass of the oxide of lead at the end, so the mass of the lead and the oxygen together. So to find the mass of the oxygen, we're going to take the mass of the oxide and take away the mass of the lead to get the mass of the oxygen, and then we can carry on as normal. So have a go at this question. So I've converted mass to mole, and then when I divide by the smallest, I'm going to get a 1 and a 1.34. Now thinking about my common fractions, which one is that like? Well, 0.34 is very like 0.33, so I'm going to multiply all my numbers by 3. When I times by 3, this will become a 3. Type that in your calculator and times by 3, and it's going to become a 4. And so our empirical formula is PB3O4. What if we're given our values as percentage composition? Well, we're just not going to worry about it. If this is the percentages here, then this is the masses in 100 grams. So we just put them in as if they're masses, and off you go. So you put them in here as if they're masses. They are, if there was 100 grams, that's how much would be that thing, and off you go. Okay, so you should have got this. Our last little section is how, when we've got an empirical formula, will we convert that to a molecular formula? So the first thing I want you to do is, as usual, put the numbers in and work out the empirical formula for yourself. So we should have got this for the empirical formula. Now how would we convert that to a molecular formula? Well, to do that we're going to need one more piece of information, and the last piece of information we need is going to be the MR. If we know the mass of the whole molecule, we'll know how many times we need to multiply up to get the actual formula. So what we do is we add up the mass of this empirical formula. So 12, add 2 lots of hydrogen, add a 79.9, and we get 93.9. And we see that in the question we were told that this had an MR of 188. So we find out how many 93.9s are there in 188. There are 2, and we double everything in that formula. So instead of 1 C, there's 2 Cs. Instead of 2 H's, there's 4 H's. Instead of 1 BR, there's 2 BRs. And that was how you would convert. Now, given that we've done lots of empirical formulas here, what we're going to do for the last little exercise is just add up this mass and see what we would have to multiply it by. So we're assuming we've done this empirical formula by that big method. Now we're just multiplying it up. So pause the video, have a go, and then come back to check your answers. So what you find there is when they're the same, you keep the formula the same. When you have to double the number, you double everything in the formula. When you have to times the number by 6, like this example, the fourth one down, you're going to have to times everything by 6.